Okay. Now, that mathematically is a perfectly idealized situation. There's no energy loss, there's no friction, nothing. So these do a fairly decent job of demonstrating this. So these masses are pretty much identical. So when this comes in, you're going to have a collision. So if this comes in, if they're the same mass, which basically are, this stops, and then this one leaves with what momentum? Same. And the same
Velocity.
same velocity, the same energy, everything stays the same. So basically, this one stops, you transfer everything to here. Nothing is lost. That's why if they're the same mass of the bullet minus the mass of the target, this stops. Now, in contrast to that, let's say that we're going to have a big, massive bullet and a small target. Okay? So when this comes in, what's this going to do after the collision?
Keep moving.
It's going to keep moving. Which direction is this going to go?
That way.
Same direction, right? But is it going to be faster or slower than this one?
Faster.
So what should happen to the distance between them?
Increase.
Should increase. So we do this, boom, miracles, yay for physics, it worked. Now, in contrast to that, let's say that we're going to have a small bullet and a massive target. So when this comes in and hits, what should happen?
It's transfers
Bounces.
some momentum
This
into
goes
the
backwards.
big bullet, and then target goes backwards.
Beautiful. So when this comes in, hits, notice that that one rolls a little bit backwards. Let me kind of do that again. That might look better. There we go. Okay, that was a little bit more dramatic. So this is when you have a small bullet hitting a large target. But what do they all have in common in terms of the sign of the new velocity of the target? Is it always going to be positive or negative?
Positive.
Positive. So no matter what happens, the target is going to go in the same direction as the bullet. Is it possible for just the target not to move at all?
I guess if the
If
mass
there is
was...
freight.
No.
No,
I had to think
bad.
I had to think about that one.
If you look at how you calculate the new velocity of the target, it's because it's twice the momentum of the bullet. So this is always going to have the same sign as
The bullet.
yes. Okay? Now, while we're here, let's go over here.
We'll hit him again.
We're just gonna do this while we're here.
Bad code.
Oh no, the camera, it's spinning.
Yeah, today is a bad and dumb day.
You're vlogging, Cohen.
This is bad. Whoop.
Cohen.
You're dropping everything.
The day just gets worse. No, I actually need you over here.
Look at the elongation. Look at the elongation. Look at it.
Okay. So the next big topic is what we call center of mass. Okay? So what I've got here is I've got two Newton scales and I've got a meter stick suspended between them. So this is 0.79, that's about 0.85. Right now they're both carrying about half the load. Okay? So here's when you get into problems like this, you have this, obviously, so this is being pulled down. So this is trying to lift that up to keep this from falling. This is trying to go in this direction, this one is lifting it up. But you also have the center mass of the board itself. So gravity is pulling down here. So if you isolate this and you make this the pivot point, then you would have two things that you would have this trying to go in this direction. Because if I just cut that string, this thing is going to fall like this. So there's a torque going in this direction, but this is balancing that out. The same thing is true over here. If I cut this string, that thing's going to go like this. Now, here's what I'm going to do. I'm going to take a 50-gram mass and I'm going to put it on this end. So right now, this is reading 0.81, this is reading 0.85. When I put this on this end, what's going to happen to the reading of that scale?
It'll go up
Why?
because there's
More torque.
More
Gravity.
gravity?
More force of gravity.
more mass.
Pulling in which direction?
Down.
Down.
Oh, the center of gravity shifts over, so that one has to suspend more of the weight.
Okay? So you're saying this one's going to go up. Do you think there's going to be a change in the reading on this one?
Yeah.
No. No.
Yes. Yes.
Because it has to be.
Increase or decrease?
Decrease. I'm
Why?
just guessing because mass is going this way. It's not like total masses.
But there's energy.
Stuff has to. The energy has to
Oh,
be.
don't throw energy into
The
this.
stuff has to be conserved.
The stuff has to be conserved.
Yeah.
That's one of the great science laws of all time, the conservation of stuff.
We all
I
love the
think I wouldn't
conservation of
do that.
stuff.
Okay, so is everybody cool with the idea that this reading should increase?
Yeah.
Yep.
Okay, so let's do this. And lo and behold, that went up to 1.36. Okay, so that was cool. This one went to 0.78.
Cool.
It was at like
0.85.
0.85.
Yippee.
So what's the only way that this reading can become less?
If there's
The center
less.
mass changes.
Kind of. Okay?
If there's less.
But look, when I put that out there, what's this board really trying to do?
Flip up.
It's trying to flip up, right? If I put enough weight on there,
It will flip up.
it will flip up.
Oh, when that reaches 0.
Oh, and that would reach 0. So this is trying to spin this way. Now, what is wrong with you today?
Nobody knows.
Bad boy.
God.
You feel bad.
So, here's the deal. Is gravity still trying to pull down on the center mass of the board?
Yep.
Absolutely, right? But now, here's you got some torque going on, right? Now, is this torque, because I've got a little bit of weight out here, just this hanger, is this still trying to make this go in this direction?
A little bit.
A little bit, okay? Not much, but a little bit, right? Now, I'm going to do this. I'm going to have everything stay the same, but I'm going to change the location. So I'm going to move this in, okay? So now, that reading has gone up to basically 1 Newton. Why?
Because it's closer to the center mass.
And there's less mass over. I don't know.
Wait. What? Wait. Yeah, it's closer to the center mass. I don't know.
There's.
Yeah.
Okay? So yeah, so look at it this way. If I put it right in the middle, what would it be carrying?
All of it.
It'd be carrying all of it, right?
The entire load. Yep.
It'd be carrying the entire load. So let's put this back out here.
It's because there was
Okay.
less. There's more torque added onto the other side.
Now, I'm going to take a 200-gram mass
Yes.
and hook that way out here.
Okay.
So that's at 1.37. This is at 0.76. I'm going to put this on here. What should happen to the reading on each scale?
Change that one.
Decrease. Change?
This one will decrease and that one will increase
Why?
because there's more torque on that one, so that one will increase. And then since there's more torque on that one, it wants to lift this side up, so there'll be less.
Okay, so we do this. So this goes all the way up to 3.04. That one dropped to 1.05. Okay? Now, here's the story. Is the system still in equilibrium?
Yes.
Yeah.
Yes. So that means when you add all the torques together, it all has to add up to?
0.
Keep that in mind. Okay, to the front we go.
Can we
should ask him about that one. Let's set the camera back now.
Well, to be honest, it looks like it's hung up already, and I just made the rule.
You can set the camera down now.
Yeah, I know.
No,
He does already too.
he'll put it close to me. and
It's more
you know
fun
what
to watch.
happens.
It's more fun to watch it through like the thing than to actually look at it.
Have the shakiest video sent to other people.
It's not shaky.
How would you know?
Colin is perfectly steady, an
Le-
unshakable rock.
Leave a comment
can
on the
see
video
it,
if you think it's
like,
if you think it's shaky.
If two things are moving at the same velocity, does it look like they're moving to each other?
You know, send that to your mom and dad and go, hey, let's talk about what happened in class
No,
today.
let's not. They'd leave me home on the Thanksgiving break vacation. Actually, no, they wouldn't. They'd like, I don't even know what they'd do. Probably something worse.
Sends you to Oklahoma.
Okay,
No.
so here's the story. So let's just work a simple example. Put that back on the.
Okay. I guess can't have any fun in this class.
Yeah,
It's a
Berg.
physics class. Of course you can't have any fun.
Yeah, Berg, you're the fun monger today. Stop.
Cohen, you're the annoying monger today.
I'm being facetious, Berg.
Isn't the fun monger like
Beat him, Berg. Beat him.
like a fish?
That was a Stephen Hawking look right there. That was like a.
That's how you looked.
Except Stephen Hawking was smart.
That's how Burger's gonna make you look.
I'm most of the way there already.
Okay.
Anyways,
We got a 3 kilogram mass and we got 4 meters per second. Hits a target at rest. So right away, you've got a big bullet and a small target, right? True? So we're just gonna see if this works mathematically, if this is a perfectly elastic collision, okay? So, to get the new velocity of the bullet, we're gonna take 3 kilograms minus 1 kilogram times 4 meters per second
divided by 4.
divided by 4, and you're gonna get 2 meters per second.
Meters per second. 4
Correct.
kilograms? What's the on the bottom? Some mass is 4 kilograms. Sorry.
4 kilograms.
For
Okay.
squirrels? What?
Kilogram.
I'm.
Don't.
It's a day. It's a day today,
You are
Berg.
on ice that's about that thick right now. Okay?
Bad.
Literally. See that?
Keep him in check.
That's what you're on right now.
Just beat him with the ruler over and over.
So, here's the story. Then to get the new velocity of the target, we're going to take 2 times the original momentum of the bullet. So we're going to take 2 times 3 kilograms times 4 meters per second. And then we're going to divide that by 4 kilograms, and we're going to get 6 meters per second. Right? Does that match with what we said was going to happen?
Yes.
Did the bullet slow down a little bit?
Yes.
Did the target speed up a lot?
Yeah.
Yes. Now, if this is true, momentum should be conserved, energy should be conserved. Now, we can do a little check. Because we said, if this is true, the sum of the momentum of the bullets, or excuse me, the sum of the velocities of the bullet should equal the sum of the velocities of the target. So I had 2 and I had 4, that adds up to 6. So those are the velocities of my bullet side. Those add up to 6. So far, that little self-check says, hey, this is valid. Okay? Now, the only momentum that existed before the collision was the bullet. Okay? That was 3 kilograms moving at 4 meters per second. That was 12 Newton seconds. So afterwards, what should all the momentums add up to? 12, right? So we said afterwards that 3 kilogram mass is moving at 2 meters per second. So we got 3 kilograms times 2 meters per second. And then we've got the 1 kilogram mass moving at 6 meters per second. So this gets us 6 Newton seconds. That gets us 6 Newton seconds. Miracle of miracles, they add up to 12 momentum is conserved. And kind of because it's Wednesday, so I'm gonna cut this a little bit short. And you can do the same thing with energies, okay? Energies are gonna be the same. Your kinetic energy only exists with the bullet. Now, here's the thing. Because this is squared, would it make any difference in terms of energy if the bullet bounces back? In terms of sign?
No.
No, okay, because it's still gonna be squared, right?
Scalar.
Now, can your momentum change sign on this deal? Can your velocity change sign?
Sure.
But your energies aren't. Okay. Now, let's talk center of mass. So this is now I'm going to kind of jump to what I was talking about with the center of mass. So if you're going to try and find the center of mass, there's a couple of different things that you can do. One is that if you happen to have something small, and if I want to find physically the center of mass, what I can do is I can start with my fingers out here on the edge. And I can bring these fingers together, and wherever they meet is under the center of mass. It would work even if I put this one here and started with this one out here. Cohen,
Yes?
am I still going to meet the center of mass?
No.
I'm not.
Oh.
Still meet at the center of mass?
Sure.
Sure. Now, what would happen if I put a 50 or 100 gram mass out there and do the same thing?
It'd be
Where am I going to meet?
A bit to the right.
closer to where the side of the mass is.
Okay? So notice I'm going to meet, not in the middle, but I'm still going to meet under the,
Center of mass.
because the board itself has mass. So if you look at this, basically you can conceptualize this also not in terms of center of mass, but also in terms of like torque. So when I met here, this board had a center of mass here that was trying to make this thing go this way. This was creating a torque trying to make it go in that direction. So where I met was the point where it's the center of mass, but also where it balances out the two torques.
The weight of the rest of that half of the board is equal to the weight of that
Yes,
half of the board.
in terms of torque, yes. Okay? Now, mathematically, mass of A times the position of A, and this is mass of B, and this will all make sense in just a second. And you can keep going and going and going, and then you divide that by the sum of the masses. So this allows you to calculate the center of mass of anything. On the assignment, you're going to calculate the center of mass of the Earth-Moon system, okay? So, let's say that you've got a board, and at 0.2 kilograms, or 0.2 meters, you have a 1 kilogram mass, and then another 0.2 meters, you've got a half a kilogram mass. And then another 0.2 meters, you've got a 5 kilogram mass. Okay? So, when you're doing the center of mass calculation, you want to judge it, these positions, from one end. These positions are not where they are from the other masses, okay? So, and it doesn't make any difference where you start. Like you guys are going to do calculations of Earth and Moon. If you're clever, what are you going to let be equal to 0? The center of the
Earth.
Earth. Let that be 0, okay? And then judge the positions from there. So, here's the story. So if you were to do this, this would be 0.2 kilograms, 0.2 meters times 1 kilogram. Plus, now, when I do that 0.5, I'm not going to use 0.2. I've got to use 0.4 because it has to come back to where that started. So that's going to be 0.4 meters times a half a kilogram. And then I'm going to have 0.6 meters times 5 kilograms. Now, before you do the math, roughly where do you think that center mass is going to be? Further to the left or further to the right?
Further to the right.
Why?
The bigger masses on
Yeah, you've got that big monstrous 5 kilogram mass. So then you're going to do all of that, and then you're going to divide that by the sum of 6.5 kilograms. And if you do all this math, I hate Wednesdays, you get 0.523 meters. So what that means is so that total length is like 0.6. So if you came at 0.523 meters and put the fulcrum right there, or brought your fingers together, that's where everything would balance out. Now, another application of this. So, let's see what they can see this board here. So, what I'm going to do is I'm going to push this board further out and further out. What's going to happen eventually,
It'll fall
right? So why doesn't it fall now?
because it's got more mass on the table,
So the center of mass is the
center of the
center of the
board.
board, right? Is there some torque being created this way?
Yeah.
Yes, this board is trying to fall this way, but the torque going back this way balances that out. So if I go a little bit farther, a little bit farther, a little bit farther, eventually that's going to fall in this direction. Why?
Because the torque of the part of the board that's overhanging the table is greater than the torque on the one that's on the table.
Beautiful. Now, what if I take a 200 gram mass and put that here?
But you can stick more of the board off the table
Why?
because you've got more torque acting
Opposing
this
torque.
way.
Yeah, I've shifted the center of mass
Left.
toward this, right? So now when I do this,
Right.
Yeah, he's right. My left.
right, I can reach that point where it just kind of balances. So notice with this one, I've got more dimension of the board out here, but this is shorter. Now, if I take this mass and move it farther back out here, now what's going to happen
The
to make
center
it
of,
balance?
center of mass also moved that way.
Yeah, so now when I shift it, then I got this. Now, what if I put it out here?
The center of mass moves more. to the
Yeah,
right.
so now what's going to happen?
When
It's-
you just a
you can
little
only
bit.
put a little, like, put less out there.
Yeah,
Before it
put
falls.
less out there.
Is this on the left or?
But here's the point. When it just begins to balance, what do you know about the torques?
30.
They're going to balance out. Okay. Talk change in momentum in rockets,
Too far.
which is what the whoosh bottle was for back there. Okay? Which we'll set off in just a second. So, you all are used to saying force times time equals change in momentum, right?
Sure.
True?
Okay.
And what did you always assume remained constant about the mass? Or excuse me, you always assume the mass remained
Constant.
constant. And it was the change in the velocity part, right?
Yeah.
Cool. That's what you all are used to doing.
Uh-oh.
Rockets work differently, okay? Rockets create force by expelling large amounts of mass as what they're consuming, oxygen, hydrogen, whatever you're burning in there. So for rockets, it's still force times time. It's still a change in momentum, but now we're going to shift the delta M. So now we're going to have change in mass multiplied by a constant velocity. Okay? So if you want to create a lot of force from a rocket, what do you want to do with mass?
Small.
No,
Big.
you want a big force. You want this rocket to consume a lot
Lot of
of
mass.
fuel, go through a lot of mass,
Huge delta M.
yes. And
Start
this
with
is
big
the
mass and
velocity
small
of the
mass.
escaping gas. What do you want that to be?
Big.
Massive.
Big. So you want
Big
to go
equals
through a
20
lot of fuel and have that gain a lot of energy, so that's being propelled at a very high velocity.
For a long time.
Yes. Now, but here's the problem. If you look at trying to get that rocket off the ground, and you want a big engine, well, you've got to consume a lot of mass. Guess what? Mass has inertia. Mass has weight. So this is where it becomes like a catch-22. You say, oh, we're going to build really big rockets. Great. Guess what?
Really big rockets have to get off the ground.
And they consume a lot of
Fuel.
And that fuel has mass and it has weight. There you go. All right, so as a demonstration of this, so,
Are we launching a rocket?
no, I'll just do it over here. That way you don't have to spin the camera.
Fun messed up like
Really great view of the ceiling.
Yeah.
Colin, after
Frankly, just
viciously
don't
shaking the
trust
camera.
Colin with fire.
What? I am very trustworthy with fire.
You know who's not trustworthy? Cohen.
Well, I'm good. I'm great with fire. I don't know about you. I've run Whoosh
He's
bottle.
completely lying.
I've never-
I don't think he's
That's a
completely
lie.
I've never burned anything ever.
Yeah.
I've
Okay.
literally done Whoosh bottle. I have done this. Whatever.
You know what?
Fine.
This thing
I see how it
sucks.
is. Oh,
Why don't you just pour the whole bottle?
that was.
No.
No.
We don't want to make the building explode.
So,
Funny though.
It would be funny.
this is basically also from a chemistry perspective, a redox reaction. Okay? So, you need the fuel, and you have the oxygen, which is provided by our atmosphere. Now, if you're going to do this, you need it in the vapor form. The liquid form of it won't burn. It's got to be in the vapor form. So that's what I'm doing with this, trying to get this area inside of that completely saturated. Now, you want the lights on or off?
Off. For
Okay.
sure.
So,
Or culture.
What chemical
Indeed.
is this?
Methanol. So. I think.
Bigger one.
What's
Okay.
the typical formula for methanol?
methyl alcohol is
Meth.
CH3OH.
Don't act like you know what it is, Gershon.
No, because
Jesus.
that thing was hydroxyl.
Yeah, you are, bitch.
All right.
Thank you.
So we also need a little bit of an ignition source.
These meter sticks really come in handy in physics.
Oh yeah, most used tool. Actually, you got calculator.
Okay. Are we ready?
Or-
Danny, get over there and catch that in case that goes that far.
Okay.
It will definitely go.
It's
that far.
always a wild
Target.
card. Okay, you ready? Nice.
Man.
No, it's okay. It's
Went
not.
out.
The paper went out. We're okay.
Paper just flew.
That was tough.
It went whoosh.
It did. It did.
Cohen, yay! We have a fire. Okay, so why did it roll? That's what we roll for him, oddly enough. Why did it roll in this direction?
Because the gas was leaving this way.
Part of it.
The momentum
Remember
has
the
to be
balloon?
conserved.
Momentum had to be conserved. The
So
escaping gas have momentum.
yes.
So therefore,
The bottle has to go that way,
go
bounce
that
out.
way with momentum.
now,
momentum
but
this
were the
direction.
particles bouncing off the sides of the barrel as well?
I would assume so.
It
Yeah.
was, because trust me, it's really warm. Okay, but why didn't it move either side?
Because it was
wheels.
equal. It was equal.
Yeah, it was equal. Where was your imbalanced force?
The front.
The front. So you had these very excited particles hitting the front, but then you had those bouncing around as well, but those
Could leave.
could leave the building. Okay, so you had particles bouncing on the front going this way. So, and here's the whole idea of rocket engines. So the more mass you can have expelled out this way, guess what?
The more unbalanced the force.
More
is.
force you're going to have. And the faster those particles are that are leaving, the more force that you're going to generate. Okay. Now, this assignment kind of has some odd random things to it because it's getting you ready for the ultimate big energy assignment, which you're going to have tomorrow. So, now, let's talk rotational kinetic energy.
I'm going too crazy.
Rotational kinetic energy is 1/2 I omega squared, right? So,
Oops.
what are the units for I? Kilograms meters squared, right? This is how fast it's going to spin, so that's in Did you wake up this morning and go, what can I do to frustrate and irritate Burkamp?
No.
Let me have a list. Let me mark off some things.
What's wrong with this? I'm not even making noise.
I don't care, you're annoying me, stop.
You don't like my prop
No.
cigar made from shop rags?
You know,
So
in
this is
hindsight-
radians per second, but that's gonna get squared, so you get kilograms meters squared per,
second squared.
otherwise known as joules?
Yeah.
Yeah. That one.
It's all
Does
Units.
force times radius equal I? Excuse me, equal torque.
Yes.
Torque also equals what?
I
fish.
I fish.
I fish.
Keep that in mind. Okay, I know y'all have to go, so stop you on the camera. Let me hand out the assignment.
we already